We're now embarking on what I think is the most exciting part of the course. At this point, we should all be pretty adept at WebGL, and now we can start looking at how we use it instead of studying more WebGL functionality. So what we're going to do in this lecture and the next is we're going to start talking about imaging applications and how we can do a lot of real-time image processing with WebGL. We'll then move on in the next 3 or so lectures after that to talking about rendering to texture, where we can do much more intricate kinds of operations. So what we're going to do is see that the heart of this is in the fragment shader. Because the fragment shader is working on a fragment by fragment basis, if we simply map our image through a texture map to the fragment shader, or make it available to the fragment shader, we can do pretty much any imaging kind of operation there. What we'll look at in this lecture are a couple of things. One is to do some standard image filtering operations that are things like smoothing, edge detection. Are pretty straightforward once you get the idea of how we can use that fragment shader. We also want to look at what we call in image processing pseudocolor, where we start with a image which is a luminance image. It's black and white grayscale image, and if we display it as a black and white image, it's not very interesting. But if we then map those black and white values into color values, we can see a lot of the information that's contained in that image in a much better way that's more suited to our visual systems. We'll also see a little bit about using multiple textures within the fragment shader, because that's going to allow us to do some matrix operations like matrix multiplication, matrix addition on some pretty large matrices. And that'll lead us to the notion of general purpose computing on using the GPU, because of the incredible floating point and parallel abilities of modern GPUs. Now, a lot of this started back when people started doing texture mapping with OpenGL and other graphic systems. So at first, when we went to raster systems, all we really did with the digital side of things was to fill polygons, but we didn't really have access to it. When we started having access to it and better, bigger, cheaper memory, then we started being able to have texture mapping and more control over the texture mapping. And then we said, well, how can we access that? So OpenGL started adding more and more texture functions. And then when we started having programmable shaders, then we had pretty much control over what we did. Now, one limitation, and we'll come back to this a couple of times, is that a typical frame buffer only has 8 bits for each color component. So even though we can do a lot of operations within the fragment shader, if all they're doing is affecting 8 bits, that becomes a significant limitation, because of, as we said in the last lecture, that becomes a limitation because we start losing accuracy when we start doing arithmetic operations on just 8 bits. Now, what happened earlier, and this was in the fixed function pipeline fairly late in that fixed function development and has since been deprecated, but it gives you the idea of what we're trying to do, is that they had something called the accumulation buffer, which was a higher resolution buffer, generally 16 bits and potentially 32 bits, and it avoided that round off problem because you could operate on a texture or some other discrete entity and then put the results inside the accumulation buffer, which had more resolution, so bits didn't keep dropping off the end and being lost. And so you could, the basic functionality was that you could multiply a texture map or an image by some constant, which was a scale factor, and then write it into the accumulation buffer, which then would accumulate, essentially composite multiple images together, shifted versions of an image so that you can do filtering, and then you could read it back. Now, it was pretty slow, though. It allowed you to get around some of the resolution problems, but it was pretty slow because the buffer generally lived on the CPU side. the application side, and so you were doing a lot of transfers between the CPU and the GPU, and so eventually that got deprecated. But a lot of the techniques you can now do, and as we're starting to get floating point buffers available as part of the frame buffer or available within the memory that's attached to the GPU, we can do a lot of these techniques. So this notion of being able to accumulate multiple images has a whole bunch of applications, and generally we put them under the heading of multi-rendering, because we do a number of rendering operations and then composite all the resulting images together. Filtering for image processing that we're going to see is the notion of convolution. If you're an electrical engineer that's done some signal processing, is easily implemented with this idea that you multiply an image by some sort of a constant, you then shift it, multiply it again, add the result in, and that gives you a filter that's operating on the entire image. But you can also do some things that are more aligned towards graphics. So we introduced a little bit of anti-aliasing in the last lecture. One technique is called whole scene anti-aliasing, and these are developed a little more in the text. But the idea here is that if I draw the line once, it may be get the jaggies and be alias. But what if I change something a little bit, the viewing, or just jiggle a little, jitter it is called, in the scene a little bit? Then when I rasterize that line, it's going to generate slightly different jagged artifacts, and when I add a bunch of them together, do this a number of times and average out the result, I'm going to effectively have applied a filter and smooth that out. And since you can do it to the whole scene at once, it then becomes a much faster process than trying to anti-alias individual lines or individual polygons. Now, related to that is this notion of depth of field. If you take a picture with a real camera, not everything is in focus because the limitations of the lens are such that even a very good lens has a limited depth of field, which is much more limited as you have a wider and wider aperture open. That gives a lot of realism and gives you the ability to create certain effects by just having certain things in focus, which your eye goes to. So one of the problems with computer graphics in general, when you try to do realistic images and animations, is that because you're doing this all digitally, you have an infinite depth of field to start with. And if you want to get the realistic effect, and you'll see this in any animated movie, what you need to do is get the equivalent of being able to have a limited depth of field. So one way to do this, and this again is worked out in the book, is to move the viewer a little bit, re-render, move the viewer again a little bit, jitter the position of the viewer, but do it in a controlled way so that one plane isn't changed. And that one plane is the plane that stays in focus when you blend those images together. So it's a very, very nice technique, again, combining the graphical 3D kind of view of the world with some digital kinds of techniques that allow you to do the compositing. A lot of motion effects are like that. If you take a picture of something that's moving and the lens is open for more than a very small fraction of time, you start seeing that blur. That blur creates very nice effects that you want at times. And you can think now, given what the two examples I just gave you, if you multi-render with an object moving, then each time you render it, that object is in a slightly different position, but all the other things that are not moving are the same. You composite them all together, and you see this blur for that. And you could do things like like render it with slightly darker for the older things, so you sort of get this idea of what direction the motion is going in. So all of those things are extensions with the idea of multi-rendering, and although a lot of the things that are supported in desktop OpenGL with multi-rendering, in particular with getting multi-resolution images, are not yet in WebGL. A lot of these things you can create totally on your own. Okay, so now let's look at images and fragment shaders. And suppose we do the following. Suppose all I'm going to do is send a rectangle to the vertex shader. Okay, that's two triangles, but think of it as a rectangle. And I render it now with an n by m texture map that I've defined as a texture object and put into texture memory. Now, suppose that, just to make this all work out very simply, that the canvas that I start with also has the same resolution. It's an n by m canvas. Well, if that's the case, then each pixel in that texture map corresponds exactly to one pixel or one fragment in our frame buffer. So I can say that the texture map is now an image, and that image is what appears in that canvas exactly. And so anything I do with a fragment shader is an imaging operation if I think of it in terms of images rather than in terms of textures and graphics. And once people started thinking that way and saying, well, gee, I can do whatever I want to that image in the fragment shader, they got this notion of what's called general purpose processing on a GPU, GPU, because the GPU has, not only does it have the parallelism and that you have multiple fragment shaders, you're also executing on RGBA at the same time, so you sort of have 4 times parallelism embedded within every GPU. But now that we're getting hundreds of processors on the GPU, we can be working on hundreds of fragments at the same time. So then people started saying, well, what can I do with that, which may not be graphics? I can do matrix operations. That was the first thing. Well, if you look at the image as being a big matrix, then you say, well, I can do matrix operations. I could do things like add matrices together by thinking of them as two different textures. So we'll look at a couple of examples of that. One is obviously anything with 2 matrices can do. Adding is trivial. Multiplying, I think, is pretty easy. If I have 2 texture maps that represent 2 images, I can easily write a fragment shader that does as an output image the product of those 2 matrices stored in those 2 textures. But you can do things that are even a little more subtle than that. One of my graduate students a while ago we did a paper on doing the fast Fourier transform in a GPU, which just really sped it up. So there's many things you can do. I'm just going to explore a few of those today. Now, the biggest single problem is, what do you do about getting the results out? Because now everything goes towards making an image. And now what do you do with that image? Well, it automatically gets displayed as part of the rendering process. What do you do if you want to get it out? Well, you can always do a read pixels to get it out, but that's going to give you RGBA, generally 8 bits. Well, things are changing somewhat. One is that we're starting to get floating point frame buffers, so that numbers are now stored, or components, RGBA components, are stored as 32-bit IEEE format floats, and so we can get those back and get a real result with some accuracy. And I suspect very soon have fragment processors that support double precision too. With that in mind, people started working on a standard for this, and the one that fits in well with all of this is called OpenCL, which understands OpenGL. It stands for Open Computing Language, which allows you to do complex operations split between computations on the CPU and computations on the GPU. The standards groups are about to come out with WebCL, which will now work with WebGL. It's interesting, and if we had more time, or perhaps in an advanced course, we'd talk about it, but it allows you to use the memory that's available. And there's a tremendous amount of memory now on the GPU or attached to it. One of the reasons we don't talk about it now is that memory is actually fairly complex. We're using it in a very simple way of just writing into a frame buffer and later to an off-screen buffer. But that memory is actually hierarchical. It's grouped into small clusters. It has 2-level caches. And to use that really effectively for parallel computation that used to go on supercomputers, but now can be done on GPU-based machines. That's what OpenCL lets you do, but you really have to understand and be able to manipulate the particular memory hierarchy of your processor. In fact, OpenGL now has, the latest one is to have compute shaders, where you have a shader now which is a little computational engine that you can send code off to do some computational work. So that's all advanced stuff that hopefully you'll all be doing at some point. Let's just look at some easy examples here. So suppose I have a texture image, which is a 1024 by 1024 texture map, and we're going to think of it as an image, so I'll call that texture object image. And then what I can do is look at the sampler. The sampler is going to return, if I give it XY coordinates, texture coordinates, then the sampler is going to return a value of that texture at that sample point. I mean, that's the point of a sampler. And if that XY is a point inside of that image, then I'm talking about the value at that image. Now, what happens if I change the X or the Y, or change both of them? Well, if I shift the X over by 1/1024th, that's 1 pixel distance, and now I have the value of the texel to the right of the particular texel that generated that fragment. In fact, we're not going to use this, but there are variables available to you within the fragment shader that allows you to obtain the location of the X in XY that generated that fragment. We're just not using it in our examples right now. So if I do that, then if any point within that texture is available to me, then I can do some operations that combine values of that single image or texture map at various locations. So here's an image enhancer. This is a very, very simple one. What that does is say, okay, if I look at the differences in the X and Y direction, that's an approximation to the derivatives in the X and Y directions, and derivatives are what determines whether something's an edge or something's not an edge. Actually it's the gradient in 2 dimensions, is where that is high, I have an edge, and where it's low, I don't have an edge. And what if I take those values and use them to determine a new image that I actually output as my fragment colors? Okay, so here's the idea. Here's a really simple one. This is on the map. I think it's called either Hawaii image, or I think it's called Hawaii image. So here, all I do, and I'm not even putting in the code for the JavaScript file, which is just typical. All it's doing is sending over a rectangle, 2 triangles. Standard way, you can do it as 2 triangles. You can do it as a triangle strip, or it really doesn't matter. So that's all exactly as we had before. What does the vertex shader do? All the vertex shader does is send everything on. So that's not. It sends the texture coordinates on. So now if I just take those 2 texture coordinates, which are really the location within that image, so here I'm just going to call them X and Y. Here's the distance. If that's a 256 by 256 image, so 1/256 gives me the spacing between texels in the X and Y direction. You can actually pass this on in as a distance, as a uniform, and then make your code flexible for any size texture image, but it's a little more explicit in this example. So here what I'm doing is I'm taking the value 1 texel to the right minus the value of my texel, so that's giving me the difference in the X direction. I'm then going to take its absolute value. I'm going to add that to the value of the texture 1 up from me, X at Y, Y plus D, minus the value where I am. I'm multiplying it by 10, and I'm taking the absolute value so that we don't have negative values of the color. 10 just gives me a scaling that looks good. And I have to be a little careful here to set the W component, the alpha component, to 1. But look at that. That's a trivial little fragment shader, and what it's doing is it's just taking some differences here to get an estimate of the gradient and displaying them instead of displaying the actual texture map. So here's what you get out of that. So here's the original image displayed just as a grayscale luminance image. We put the same values in for RG and B, so that the example that I started with here is really doing everything in 3 or 4D, but it's using the same values for X, Y, for R, G, and B. It's essentially free because we use parallelism in the GPU. Here's what you get by enhancing that with that fragment shader, and you notice this is the area around Honolulu. Here's Waikiki Beach. This is Diamond Head over here. Notice how enhanced this is. How here's Cocoa Head showing up, which you can barely make out over here, and you could, if this was a little brighter, you'd actually see the shoreline here. So that's a really simple, and it's real time. If this image, the texture map was changing every image, every rendering cycle, every 60th of a second, this would be changing every 60th of a second. So it's a real-time image processor. Now we could do a little slightly more complicated one. I just did. It took me about 5 minutes to change this program to one which does a Sobel edge detector, which is nonlinear. And the reason I wanted to show you this is the first example is kind of a linear example, filtering, and we just take an absolute value to display it. This one is a little more complex, but also works very, very rapidly in the fragment shader. So what this thing does is take a smooth gradient at each point, and the way it does it is it takes 3 differences in the x direction and 3 differences in the y direction, weights them more towards the center, and that gives me a smooth gradient in the x direction, a smooth gradient in the y direction, and I use them as the x and y components of the actual gradient, which will point in a different direction. And I take the sum of the square root of the sum of the squares of the x and the y calculations I did here, and that again is really simple with a fragment shader. Here's the fragment shader over here. So it's using 3 points above the point I'm talking about, 3 points below to get the gradient in the y direction down here, 3 points to the right, 3 points to the left to get the gradient in the x direction. The center one is multiplied by 3 in both cases, so you get a center weighted average. And down here, I simply take the square root down here. Actually, I don't even need this last line. I put the 1 in over here, and here's what you get out of that, which is a much, much prettier image. Look at that. And again, this is real time. If the underlying imagery, so if you're doing something like you had a bigger underlying image and you wanted to have scroll through it, in real time you would be getting this enhanced kind of image here where you see the craters really well, you see the crests of the little hills over here really, really nicely. And you can do all kinds of things. You can color that, as we'll see in a few minutes. Now, next thing we'll talk about is this idea that you can use multiple textures. Since we support multiple texture objects with the GPU and WebGL, there could be multiple textures available to the fragment shader. So if I have 2 of them and I look at them again as being images in the same way, then if the fragment color is the sum of those 2 textures, I've effectively done a matrix addition on a fairly large matrix. Now, by the way, notice in all these examples, and we're going to keep seeing that the vertex shader basically does nothing. All you're doing is generating that initial rectangle to get this whole process started. Every time you want to update, you generate this rectangle again. It doesn't change, but the action is all happening in the fragment shader, but we need that vertex shader, and before that the application to say, hey, I need to render again, and do that. So if you look at how big you can support, some of these new GPUs and graphics cards support textures that are up to 8K by 8K. And it's even better than that, because the examples I've shown you are not really using RGBA, they're actually just luminance images. So I know that the way the GPU works is it does the red, green, blue, and alpha components in parallel. So I'm really not even using that 4-way parallelism which is built in. So if I now say, what if I put the red component, so I have a really big image, suppose it's 16K by 16K, and I just divide it up into quarters, make this top left quarter the red, this top right the green, likewise the bottom left for the blue and stick the bottom right components in the A. Now when I do whatever imaging or matrix operation I want to do, matrix addition, matrix multiplication, I'm now can operate on things that are twice as big in both the X and Y directions in the same amount of time because it's doing it 4 ways automatically. Okay, so this is really the heart of what people are using for GPU. We're going to do a lot more when we start being able to render to texture and save things and then use the results of one rendering to affect the next rendering. As we're doing them here, every rendering is completely independent of the previous rendering. Now I want to add one more thing to this, which is what about color? We've been doing luminance images and they don't look that great as black and white images, but I'm not using really the power of color. So what if I simply took the values that I had there? Now they're going to be the same as I've done them, stored in red, green, and blue. And what if I take those components and treat them differently? So I do some kind of processing to the red image, some other processing to the green, and some other processing to the blue. Then, rather than always having red, green, and blue be the same for a given fragment, they're now going to be different. So here's one that simply does something symmetrically about the halfway point. This one, so that gives me, I do this for the green. What I do, since the blue starts off as being the same as red and green, 1 minus color dot this just inverts the blue and leaves, and I haven't done anything to the green, which is just the luminance image, but I formed a color which is not a gray value for every value that's passed in. And you can think of that as functions for each component. You can think of that as the luminance values as being indexes into this function which produce colors. And in image processing, that technique is known as pseudo-color. It's essentially what we do with index color, which isn't used much, but it is used here because if you have a grayscale image, often you do want to do it. So here's one example of that. This is that hat function we used for displaying meshes, and if you look top down on it, it would be bands of alternating from white, going from white to black, black to white in a sinusoidal way, finally dying out. This is 2 different, slightly different color maps of it, and it's a much, in this case, it's a much prettier image. I probably should have done that to the Hawaii image too, but allowed you guys can do that. So the next step is to really say, well, what's really left out here? Well, really the biggie is we've shown simple filtering. We haven't shown our ability to iterate because I really haven't shown you yet how to store it. And it's really the combination of using texture memory and off-screen rendering that's really going to be the key to being able to do far more complex and interesting things with GPUs. The thing that really puts it all together is really this thing, is that if you really want to do complicated things, you really need to be able to work more than on a pixel by pixel, one location at a time basis. Some problems fall into that domain, but the most interesting problems don't. And the heart of this is that you need to be able to store things, but you really need shared memory. And if you look at what's shared, is none of the geometry is shared. I can't, when I'm on a given polygon, I don't know anything about other polygons. But what is shared among all the geometry and all the vertices and all of the fragments is they all have access to the same texture memory. And so the trick here is to look at methods, which we're going to be doing, which use the texture memory as shared memory that's available both to the vertex shader and to the fragment shader. But first we're going to look at an application of generating the Mandelbrot set in an incredibly fast, efficient way, a great example of doing imaging with WebGL and imaging operations.